All right, today I'm going to talk to you about polar change of variables. So this is going to be really useful for us in a situation where we're going to want to integrate over a region that's like kind of round. Last year we did some polar integration in AP Calculus, and it kind of seemed like, well, kind of seemed a little tedious and unpleasant. It's like, well, why would you need a polar curve unless you already were given a polar curve? And I think anybody that's taken a physics class can see the need to integrate over a kind of a circular or a round region. And then this is kind of just the first of a few types of change of variables we're going to look at over the course of this class. So kind of the motivating situation is you've got a region like, say for instance, the unit circle. And you want to integrate over that circle. Just show you how this kind of would go if we were going to try to do this with rectangular coordinates, right? If we were going to do this, I can write the bottom half of the circle as y equals the negative square root of 1 minus x squared. And up here, I can write this as y equals the positive square root of 1 minus x squared. And so if we were going to want to integrate this thing, we need to, so if I'm going to let y be variable with respect to x, I'm going to have to do dy and then dx. You could go the opposite way. You could say x for the left half was the negative square root of 1 minus y squared. It wouldn't really change what I'm saying here. What I'm saying is that, x is going to run from negative 1 to 1, and y is going to have to run from negative square root of 1 minus x squared to the positive square root of 1 minus x squared. And then we're going to start with y equals these things, and then x equals those things. You can see what's going to happen here. You're going to cook up an antiderivative for f with respect to y, and then we're going to plug in these things, and then we're going to try to antidifferentiate that with respect to x. That seems unlikely, right? It doesn't sound like I'm going to be able to find an antiderivative for this in general. And I'll show you that, really, if we think about polar coordinates, this is r ranging from 0 to 1 and theta ranging from 0 to 2 pi. And we think about when we first started double integrating over a rectangular region was super easy because that necessarily meant that all four of these were just real numbers. And that would be kind of the same idea with polar, is that it'll make our integration much, much easier. Okay, so what I need to do is I need to get basically a formula for dA in terms of r and theta, and that's what I'm going to do now. All right, so I'm going to start off with, I've got some kind of like area here. And what I want to do is I want to get, like a small piece of area for the grid that we're looking at, right? When we were looking at the Cartesian grid, it was, it's kind of the grid pieces were squares. And, we could think about this is delta x and this is delta y. But this grid is a little different. It's like kind of it's like a crust of a piece of pizza. And so what I'm going to do is I'm going to kind of just take a small little bit of area here, and I'm going to bring this out and kind of draw on this a little bigger. All right. So, and I'm gonna rotate it a little bit. I don't think that'll make a huge difference for y'all. I think you'll still buy what I'm saying here. Okay. So I've got this small area here. Okay, this is pretty clearly delta r. And you might be tempted to say that this is delta theta, but this is going to be more than just delta theta. It depends on how far away from the origin we are. So I'm going to kind of draw. That wasn't the best straight lines I've ever drawn, but say that this is the origin right here. Okay, this right here is going to be delta theta. And now I need to remind you of a fact that you knew in geometry and probably in pre-cal a little bit about the length of this. So I'm going to talk about the length of an arc of a circle. Okay. so we know it's going to be a proportion of 2 pi r, right? We've got a circle with radius r, and we're interested in, say, how much length is here? Okay. And what we can say is that, this length is going to be some proportion of the whole circumference, which is 2 pi r. So, and, I think, even though at this point you're really experienced with radians, I think it's always good to call back to the idea of degrees. So I'd say I've got some number of degrees here, some theta degrees. And so we'd say theta divided by 360 to get the proportion, right? But we're not going to talk about degrees in this class. You already know that. We're just going to change 360 into 2 pi. Okay. So the length of the arc when theta is measured in radians is just the number of radians times the radius. Okay, that's kind of like why we chose the radian measure to be the way it was. Okay, so that means that if this is like on R1, say R1 and R2, this is going to be R1 delta theta, and this will be R2 delta theta. Where probably I don't really mean the same R1 and R2. I probably should have said F1 and F2 of theta there. But I just have one R and a different R. Call it RA and RB if you will. Okay, so at this point, I'm going to say that we're interested in letting delta area get really small, right? And in order to do that, we're going to need delta R and delta theta to go to 0. Okay. Now specifically, as delta R goes to 0, these two arcs are going to kind of get closer to each other. They're going to approach a single length, right? As delta R goes towards 0, and so we're just going to call that R. That's what I'm saying. So in the limiting case, we've kind of got something that is getting closer to rectangular, and it's going to be R delta theta times delta R. And now as these things go towards 0, we're going to have, and this is kind of like the big result that I'm going to put over there, the thing that you're going to need to remember in the same way that you needed to remember last year that we found a polar area by integrating 1/2 r squared d theta. This is exactly the same thing, and I'll reconcile it with that here in a moment. The big result is that dA is equal to r dr d theta. Now I'm going to draw you a picture of of a theta simple in an r simple region, but I'll tell you the vast majority of the time we're going to be looking at r simple regions. Just because the likelihood of you getting a polar curve written as theta of r is, it's very rare. So almost always it's going to be the order of integration will be dr and then d theta, but not always. Okay, because I've got these pictures for you. I was just going to draw you a quick little image of an r simple and a theta simple region. I think I'm going to just say that this is an r simple region. I'm going to get a different color. So this is what I would call an r simple. Right, because theta is between two numbers and r is between two functions of theta. And then theta simple is going to be kind of the opposite, and I'm going to need to draw you a picture of this. Wedge myself in here, but this will be good. R is going to be between two constants, and theta will be between, some kind of like functions of R, which could look like that. I don't know. And so this is theta simple because R is running between two numbers, and then theta is going between two functions of R. And I'll just write that. It's kind of occurring to me, I feel like the nomenclature here seems a little backwards, but I'm just going off of what I saw in the Larson textbook. I had never kind of thought of the difference here because, you know, almost always we're going to be looking at regions like that. Okay. Especially round things. Going to be R simple for sure. Okay, the next thing I want to tell you, I'm going to do some examples, and I want to talk about, you know, polar area from Calvisium. That's going to be my first thing I want to do. Okay, so remember last year we said that the area of a region, a polar region defined by like R of theta, which maybe I'll say was one of those ones that we really kind of liked to do in AP Calculus. We'll call this F of theta. Okay, and if we wanted to find the area in here, remember kind of like the result we had was we needed to integrate 1/2 R squared, so 1/2 F of theta squared d theta. Okay, and I'm going to, you know, propose that that's going to be what we get when we do this the double integral way. So remember from you know, last time, or you know, a few videos back, finding area using a double integral, we just double integrated dA on the region we were interested in. So if this is my region R, the area of R is the double integral over R of, hold on, oh, it's just dA. Right? You integrate dA to get A. And now I know that dA is R dr d theta. R dr d theta. And now R is running from 0 out to F of theta. And theta is going to be running from 0 to pi. But in general, you could say it was running from theta 1 to theta 2. I'll just say 0 to pi because that's clearly what we're looking at here. And then when I actually integrate R with respect to R, I get 1/2 R squared as R runs from 0 to F of x. So okay, and then when I actually plug that in and, you know, subtract and stuff, I'm going to get the integral from 0 to pi of 1/2 F of theta squared d theta. Now, if you were interested in like, oh, wait a second, didn't we also do, you know, like the area between two curves? Like basically in calculus, we could have found the area of this region right here. And yes, and that would be if we just let it run from like F1 of theta to F2 of theta, and then we would just get the difference like we did last year. Okay, but you know, after squaring. So I was just going to show you that that's where it comes from. And then the last example I want to do for you is volume of a sphere. Now, I'm going to do this for the unit sphere, just kind of keep it pretty concrete. But you can just replace my ones with, you know, like a row or just some like kind of fixed variable a for the radius. And you can show that for any sphere, the volume is going to be 4/3 pi r to the third. All right, so volume of sphere. And hopefully this also shows you why you would want to do this in the first place. Okay, because if I've got a sphere, it's not a sphere, just not a good way to draw it. I think you gotta start with the sphere and then put the axes in. All right, so that's gonna be my x. Here's gonna be my y. Like this should probably be that way, and then here's, regardless, kind of the equation for this is going to be z squared equals x squared plus y squared, right? Meaning that z is the positive or negative square root of x squared plus y squared. What I'm going to do is I'm just going to say z is the positive square root, and so I will only be considering this portion of the sphere, right? And so I'll just double the volume I get here to get the total volume of the sphere. So what I'm going to do is I'm going to say, well, this is going to be twice the double integral over region R of, and so I'm going to have to figure out what region I'm sitting over. I think you can probably see it's the unit circle. The double integral over R of f of x dx is going to be volume. So the square root of x squared plus y squared, and then, well, let's just say dA. Now, again, if I was going to do this rectangularly, I would have to say that, y was running from the negative square root of 1 minus x squared to the positive square root of 1 minus x squared, and x was running from negative 1 to 1. And this is an antiderivative that can be taken, but it's one that you have to look up from a table, and it's very unpleasant. And then the likelihood of us throwing those square roots in and being able to antidifferentiate that, I don't like it. So what I'm going to do instead is I'm going to change to polar coordinates. Okay, this is going to be great, right? Because I'm going to still be integrating the same function, but this is where, over R, and maybe I can just draw you a picture of R. Okay, so R is going to be the unit circle. And that means that R is going to run from 0 to 1, and theta will run from 0 to 2 pi if I go to my polar change variables. Also notice that the square root of x squared plus y squared, that's also R. So this is going to be really nice. This is going to be twice the double integral of, this is R, and dA is R dr d theta. And okay, so R is going to run from 0 to 1, and theta is going to run from 0 to 2 pi. Okay, this is R squared. I'll get 1/3 R to the third. Maybe I'll put that 2 back in. And I'll get 2/3, R to the third, as R runs from 0 to 1. Okay. We're going to integrate that from 0 to 2 pi. Okay. This will be, what am I going to do? I'm going to plug in 1, I'm going to get 2/3, I'm going to plug in 0, I'll get 0. And so I'll have the integral from 0 to 2 pi of 2/3 d theta. Antiderivative for 2/3 would be 2/3 theta, as theta runs from 0 to 2 pi, which is going to give us 4 pi over 3. Okay, now, if I wanted to show this for any kind of sphere with radius a, I would have replaced this with a. I would have induced basically an a here, and there would be 4 pi over 3 a to the third. That's what you would find. Okay. I think that's all I got to say for you. There's going to be some examples where you'll, do other things with polar change variables, but this is, I think, good enough. And then, of course, the most important thing that you need to remember is that dA is R dr d theta.